This conference will now be recorded. This conference will now be recorded.
So very good evening, students. Today we'll be discussing numerical problems from previous year's exam paper on the chapter electromagnetic induction. So this is a problem from JEE paper 2013. This is JEE mains 2013. Okay, so let us read the problem first. So this is from electromagnetic induction. So there will be magnetic flux, Faraday's laws of induction, and then Lenz's law, self-induction, mutual induction, etc. Motional EMF. Those things will be there in this, and there will be further transformer, etc. A circular loop of radius 0.3 centimeter lies parallel to a much bigger circular loop of radius 20 centimeter. Parallel to a much bigger loop of radius 20 centimeters. The center of the small loop is on the axis of the bigger loop. The distance between their centers are given as 15 centimeter. If a current of 2 ampere flows through the smaller loop, then the flux linked with the bigger loop will be what? So basically the problem is like this, that there are two loops. This is bigger loop. Let's say this is the let's say this is the center of the bigger loop and this is the axis of the bigger loop. Bigger loop has radius 20 centimeter. If we require, let us say this has bigger loop has radius capital R, which is 20 centimeter, and there is a smaller loop which has radius small r, say small r is equal to 0.3 centimeter. Now the center of the smaller loop is on the axis of the bigger loop. This is what is the problem. Now the question is that if 2 ampere current here, 2 ampere current flows, let us say this is flowing in the anti-clockwise direction itself. If it flows through this smaller loop, then what will be the link in this? Basically, this is a problem of mutual induction, and you know this is like there were series of experiments performed by Faraday and Henry. So this is one of the experiments. So if the current changes over here, then flux will be also changing, and there will be induced EMF, etc. We have learned. So how to find out the flux link in this? So first of all, let us say this is loop 1, this is loop L1, and this is loop. Okay, let me just go to the next page, or let's say let us be here itself. So you look here, what will happen? This is a loop. So if current flows through this smaller loop, there will be magnetic field produced. This is a circular loop, and it will produce magnetic on its axis. Okay, and then that magnetic field will be always actually, suppose this, if this is the loop, it is, suppose this is uh, standing vertically with the horizontal plane, so and current is anticlockwise direction, then magnetic field will be actually in this direction. Okay, so there will be magnetic field like this, magnetic field lines will go like this. Okay, and this distance is given, this distance, say this is some x distance. Okay, let us say this is x distance. Okay, so what is the magnetic field produced by this smaller loop? Since current is flowing through the smaller loop, then it will produce a magnetic field at the center of this bigger loop. Okay, what is the magnetic field? So field due to the current loop 1 at an axial point, we can find out, this is smaller radius. Okay, so we know the magnetic field will be B, let us say B1, it is created by loop 1 at this particular position at the center of this. So it will be mu0 and flowing through this. Let us say this current is I1, say this is I1. Okay, so mu0 I1 is I1. Okay, so mu1 is the a square into a square, that is square. Okay, radius square divided by 2 into the radius square plus x square whole to the power 3 by 2. So this is the magnetic field created by the loop 1. Okay, so the flux with the loop 2 will be phi 2. Suppose this phi 2 will be phi b1 into a 2. Okay, so b1 is this one, mu0 I1 r square divided by 2. Okay, into, there will be pi capital R square. Okay, so this is the phi 2, the flux linked with the bigger coil. I'll go to the next page. Similarly, if we want to find out, okay, let us see this x distance is given, right? The radius is given, this radius also given, then it is easy to find out the flux from here itself. We can just do it. So phi 2 is equal to u1 into a means, so we know mu0 I1 small r square divided by 2 into whole to the r square plus x square by 3 into, yes, so this into pi capital R square. So this is the flux. If we put the values, suppose this I1 was given as, see, I'll write the values. I1 was given as 2 ampere. Mu0 we know 4 pi into 10 to the power minus 7 with proper unit in SI unit, and small r was given as 0.3 centimeter. Okay, 0.3 centimeter, if we make it meter 10 to the power minus 2. Okay, this will be, and what else, x is given as 15 centimeters, so 15 into 10 to the power minus 2 meter. Okay, so capital R is given as 20 centimeters, so 20 into 10 to the power minus 2 meter. So if we put all these values, so say 4 pi into 10 to the power minus 7, then 2 into r square is 0.3 to the power minus 2 whole square divided by, here there is a 4 pi. Okay, so here again there will be a pi here, and r square is 20 into 10 to the power minus 2 square, this square, okay, divided by 2 into again 0.3 into 10 to the minus 2 whole square plus 15 into 10 to the power minus 2 square. So this is whole to the power 3 by 2. If you solve it, if you solve this, what you get is you'll be getting 9.11 into 10 to the power minus 11 Weber. Okay, if you solve this numerical calculations, then you get that. Okay, so we can say what is the option? Option first one will be the correct one for this problem. So it was a very simple problem, not that tricky. But anyway, let us go to the next problem. This is the next problem. Here, in a coil of resistance 100 ohm, so there is a coil, it has 100 ohm resistance. 100 ohm resistance. A current is induced by changing the magnetic flux. A current is induced by changing magnetic flux through this, as it's shown in the figure. See, this is the current which is changing with time. So this current change will actually induce an EMF here, because there will be change in the flux because of the changing in current. So magnitude of the change in the flux through this coil, you have to find out what is the change in the flux through the coil. Let us first write what is EMF. EMF is equal to, actually I am writing this modulus. So d phi by dt. This all of us know that this is Faraday's law. So change in the flux will give you EMF. I'm just taking the modulus. Again, if there is a current flowing through, suppose I current is flowing through the coil, so this E can be written as again I into R. Okay, I into R. Now look, from this we can write d phi, that is change in the flux, will be this. Okay, so d phi is the change in the flux in the coil or through the coil, that is equal to E into EMF into dt. Now again, from this relation we can find out this E is equal to IR. If we put it here, IR, put it here, look, d phi by, okay, d phi, that is the change in the flux, that is equal to, E dt, that means IR dt. Okay, now if you want to find the change graphically, see, this is the graph shown how the current changes with respect to time. So that is shown, but the resistance being constant, I can write this. This is a variable quantity, this is a constant quantity. Okay, so what is this IDT? IDT actually will give the area under this curve. So I dt will be changed. That is the area under the curve itself. So what is the change in the, then therefore the change in the flask will be R into IDT means area under the I versus T curve. Okay, area under this curve. So what is the area under this curve? Suppose say A means half base into height. Base is 0.5, half base into height. Height is 10 square. Okay, so this gives you, so this gives 25, this area here from here, this meter square into this R will be again 100 ohm. So what we get is actually, sorry, this is OA bar, not what. So 250 Weber. So this is the change in the flux. Change in the flux through the coil will be 250 Weber. We'll go to the next problem. See here in this problem, a 10-meter long, I'll tell you what this problem is also the previous problem which we have solved already. That is from so what was the problem? Okay, this 250 OA bar. This was actually from 2017 JEE Mains problem. Second one was JEE Mains 2017 problem. Okay, now we'll move on to the third problem. This problem is actually from 2019 JEE Main. Okay, this is a good problem. Let us see what it is. A 10-meter long horizontal wire extends from northeast to southwest. Let me draw it. This is north, this is east, this is west, this is south. So southwest is this part and northeast is this part. So there is a wire which is actually extended northeast to southwest. Northeast to southwest. Like this. Okay. Now the question is, it falls with the speed 5 meter per second at right angles to the horizontal component of the Earth's magnetic field. Okay, at right angles. The magnetic field is given here. This is the Earth magnetic. This is 10 to the power minus 4 wave per meter square actually. The value of the induced EMF of the wire is what? So in this case, when the horizontal component of Earth magnetic field is at right angles, so right angles, let me say it is falling with speed at right angles. Okay, at right angles to the component of the Earth's magnetic field. Then the magnetic field, Earth's magnetic field horizontal component of Earth's magnetic field is given BH is equal to 0.3 10 to the power minus 4 Weber per meter square. So in this case, BH is given. So BH can be treated as B, okay, or the magnetic flux index, magnetic flux. This is Weber per meter square, magnetic flux density, and the speed V is given. It is falling in this magnetic, okay, this much meter per second, and what else? Okay, wire has length L is equal to 10 meter. Okay. So since the wire falls perpendicular to the horizontal component of the Earth's magnetic field, so induced EMF can be actually found out from the motional EMF formula for motional EMF. What is the motional EMF? Motional EMF. Motional EMF is B, V, and L. Okay, B, V, L. Okay. So BVL in this case, B is given, V we know, and L is also 10 meter long. So with that, since it is actually perpendicularly falling, okay, it is falling perpendicularly with the horizontal component of the magnetic field. So that's why the magnetic field so say EMF will be actually component of the force. So the value of induced EMF will be is equal to BVL. So BVL, this expression you have to put what is B, what is V and L. B is 0.3 into 10 to the power. V is 5 meter per second and L is 10 meter per meter, 10 meter. So BVL. So this is 15 into 10 to the power minus 4 volt and or 1.5 into 10 to the power minus 3. Okay. So the first option will be the correct answer. Here actually the point is Earth magnetic horizontal magnetic field, and then you have north, east to southwest. The wire is, so these are actually to confuse you somewhat, but here what you need to know is BVL or motional EMF. Since this is falling perpendicular to the magnetic field, that's why we have done this. So there is a nice question over here. The fourth question. Here, the self-induced EMF of a coil is given. self-induced EMF. We know self-induced EMF is equal to minus L di dt. Okay, or if we take the magnitude, then this is positive. Anyway, the current in it changes at a uniform rate from 10 ampere to 20 ampere. So current changes in 1 second. The change in the energy of the inductance. So you know there is inductor coil. There is an inductor coil through which the current is changing from 10 ampere to 20 ampere, and the self-induced EMF of the coil is given. Then when the current changes like this, what is the change in the energy associated with the inductor coil? Let us see from here that L di dt is equal to this. So here di in the sense the change in the current, that will be here 25 minus 10. So this is 15 ampere change in the change in the current. And what is this dt? Dt is actually given as 1 second. Then we will be able to find out E by di by dt. So this E is given as 25 volts, right? EMF. Di is 15, di by dt 15 ampere per second. Okay, per second, so second will come here. So volt second will be joule, right? So this will give you 5 by 3. This is Henry. Okay, this is in Henry. Now, what is the energy stored or energy associated with an inductor? So energy will be actually half Li square. Half Li square. So half Li square means this is delta I square, the change in the current, square of the change in the current. So half L means what? L means 5 by 3 Henry we have got, and half L di square. So 25 square minus 10 square. So this will give you 5 by 6 into, this is 5, 6 to 5, 5 to 5 actually. So 600, 625. Yes, this is 100. So this is 525. Okay, 525. Now, if you solve it, this simplify it, what you get, you'll be getting this particular value. Okay, this is very simple. What was the clue point here? The clue was here in this situation. How do you write EMF, induced EMF for an inductor coil? So that is L di dt. Okay, so let us move on to the next problem. Here, the problem is related to solenoid. So far today we are taking only the flux linked from the first portion of the chapter. You can see first portion of the chapter. So this fourth question also from actually JEE Mains 2019. This problem also was JEE Mains 19. The total number of turns total number of turns and cross-sectional area in a solenoid is fixed. However, its length is varied by adjusting the separation between windings. Okay, that means you have solenoid like this. You have solenoid. So it said that this length actually, like length has to be taken like where the windings are there. This is L according to this problem. See here, you may take the core for long. You can take a core long to core, doesn't matter. But the length of the solenoid will be taken as that portion of the core only upon which the turns are there. Now this L can be varied by changing the distance between the coils. These coils, okay. So if I just make it like this, so this actually has changed, but this change has to be uniform anyway. So the question is like that, just by changing the separation between the windings, the L is varied, whereas the this number is not changing, it is constant. The number is constant. And cross-sectional area also constant. These are the things given. Now I have to find out the solenoid, like the inductance of the solenoid will be proportional to. Okay, so let us see for a solenoid, we know B is given as mu0 in I. What is this mu0? Mu0 is the permeability. Fine. This capital N is equal to this by L into I. So the total number of turns are constant. That means N is constant. Now let us say inductance of the solenoid is proportional to. Again, this we know, this will be B. So if I write B into A, this will be phi. So this phi will be exactly equal to L into I. So this L, let's say this L is small l. This L is self-inductance. Okay, so self-inductance is this L. So phi is actually, so Li is equal to phi. That is what we will write. Phi means B into A. We'll write A is actually the loop area for each. So our area of cross section of the solenoid itself. So this is B is mu0 in I into so mu0 in I. This is a magnetic field for the solenoid, and area is actually phi into, or let us say just A itself. And what is this small n? This small n actually is capital N by L I into A. So you can see this part I can write as mu0 n by L, mu0 n by L into area. This is whole into this into I is equal to I. That means this part, if we just compare left and right hand part, then we can obviously say mu 0 n A by L is there, small l, mu 0 n A, so n by L, mu 0 n A. Okay, anyway, so this is the inductance. This is the self inductance. So the self inductance L is proportional to the length. Here the question was how okay, let me just erase now this portion. All of you know this. Let me just erase this part. So we have got, see here the options are actually how it will be, whether it will be proportional to 1 by L, 1 by L square, or it will match with L, like it will vary with L, it is directly proportional, or D option was there. What is the option for D? D is L square. So we can see this has magnetic flux. So the self inductance depends directly on the length of the solenoid. So this is the self inductance, or inductance simply. So this actually vary with okay, so 1 over L. This first option will be the correct answer for this question. Now there are two coaxial solenoid of same length. So this question is also from 2019. Okay, so previous one also was from 2019, main 2019, J main 2019. So here let me tell you the options. The options are given as N1 by N2, option A, N2 by N1, into R1 by R2. Option B is N2 by N1, R2 square by R1 square. Option C will be N2 by N1, and option D is N1 by N2. Okay. So these are the options. The question is, there are two coaxial solenoids of same length L. So coaxial solenoids, okay, you know, we have already read in the textbook. So there are two coaxial solenoids. Suppose this has radius R1 and the bigger one has radius R2. Okay. And the numbers of turns are actually N1 and N1 in the inner one and N2 in the outer one. Okay. So N2 here, N1 here. Turns are there. So there, the rate of mutual inductance, oh sorry, the ratio, this is not rate, this is ratio of, this is ratio, this is ratio of mutual inductance to the self inductance of the inner coil is how much? So that you have to find out. Now the question is, if you find out what is mutual inductance, what is self inductance, if you can derive, that is good, but that may take longer time. So the only point is here, like only thing is that you can do, you can just directly remember what is the mutual inductance for two circular coil. So mutual inductance will be mu0 n1 into pi, since it is for inner coil, it is pi into r1 square. Okay. And what will be the self inductance? Self inductance will be mu0 n1 square into pi r1 square. Now if you take the ratio, because they have asked you to find out the ratio only, the rate of the ratio of mutual inductance to the self inductance. So ratio of mutual inductance to the self inductance will be mu0 n1 into pi r1 square, and this is mu0 n1 square pi r1 square. Okay. So here it is pi r2 r1 square itself. So look, mu0 goes up, n1 will go up, so n2 by n1. This pi goes up, r1 r2 square. So both are r1 square, right? So both will be actually cancelling each other. So finally what is remaining is n2 by n1. Okay, n2 by n1. So what is the ratio of mutual inductance to the self inductance, that is n1 by n. How do we found out? You need to know by n1. How you need to know what are these quantities for a circular loop. Okay, so with this we'll stop it here for today. We have solved 6 problems today. So next day again we'll take up. Next day means Sunday, take up more problems on this electromagnetic induction part. The then finish slowly. So thanks. Bye for today.